So we already saw that there is a hint or a pseudo algorithm or mechanism that would allow us to go back and forth between from tables to classes or from classes to tables. Right? We saw that if we have foreign keys, that looks like it has something to do with being a weak relationship, a star, or if we have a one in cardinality, typically that perhaps means that there's a primary key on that side. Okay, so to go from tables, from class diagrams to relational model, or vice versa, we're looking for an algorithm to do this, right? So for instance, let's just take this one, this really simple one where we have a CD, we have a track, and we have these tracks are referring to the CD, and we have lyrics, right? Where a lyric is all the words to a particular song is referring to a particular track, right? Saying that these are the lyrics for that particular song, right? So notice that here's something that is somewhat new. Notice that here are the nomenclature here is that the primary keys are bold and underlined, right? Whereas the foreign keys are italicized. Yes. So here with foreign keys are bold and italic, and the foreign key are italic. Yes. Whereas notice lyrics over here, it's bold, underlined, and is italic. So it looks like this track ID is actually both a foreign key and a primary key. See that? Meaning, I am unique. Okay, I am unique, but I also am referring to somebody else, right? So this is the way we're going to be able to implement a one-to-one, right? Saying that if the track has a particular value, I have that same value, right? And I can only be that value, right? So whatever you are, I am too, okay? And I am referring to you. So if one changes and the other changes, so I'm establishing a one-to-one relationship between the two. There's only one lyric for a particular song, okay? Right. So yeah. So that's what I meant here, right? So the lyrics have it's both a foreign key and a primary key, which establishes a one-to-one relationship between the track and the lyric. Yes. You could, exactly, and that's a good thing that we'll come back to. That's a valid point. Only if it only if the data makes sense that it lives also over there. For instance, it could be that a student might have a permit, right? And I have only one permit. Yes, and so you might ask, well, why doesn't the permit information is also as part of the student? And you might say, well, because it's not really part of the student. It's not defining the student. The permit does not define the student. It's a concept unto itself, and it just happens to be related to a student, right? But it does not necessarily logically live as part of the student, right? So it might be, right? So it's a good point, right? That you might decide to incorporate it or not, right? If it makes logical sense. Here we do have a many tracks for one CD. We have a one lyric for one track, right? So some of the constraints that we have identified. We also have a one-to-many relationship between the CD and the track, meaning one CD is going to have a whole bunch of tracks, but we have one track for every one lyric. So there's a one-to-one there. Here's an example of how this might look like. We have a particular CD, 1, 2, 3, having many tracks, 1, 2, 3 over there, or 2, 3, 4, several tracks. But then when you go to track and CDs, there is a one-to-one relationship between the track and the lyric, right, that is associated to that particular track. So the database, as we mentioned earlier, that the ones and the stars, right, they might give us a clue on what the primary keys and foreign keys, on which side do they stand, right, and that the lines are really capturing the relationship between the two, and we don't typically capture foreign keys and primary keys as part of the attributes of the UML, only if it makes the conversation with our audience more clear, we would add these fields. Yes. So here's a pseudo algorithm that would allow us to go from a relational schema, from a set of tables, to a class diagram, right? If you're given for every table that you have, I'm going to just blindly create a class, right? And the name of the table will be the same name of the class. The other one might be that if a table 1 has a foreign key, then so if table 1, so we have here table 1, and we have table 2, and we have here that there's a foreign key here. We have a foreign key that is referring to a primary key here. Then the annotation, so these will be converted into the following classes, T1 and T2 from the first step, right? So this is the relational schema. This is relational, and this is UML class diagram. So that's the first step. And so if the table 1 contains a foreign key to table 2 that has a primary key, then there would be a line between the two, and there will be a star. There will be a 1 on T2. So there's a 1 right here, right? Now I need to know about T1. What do I do with T1? If the foreign key is just a plain old foreign key, right, then it's a star. But if it's a foreign key, it's also a primary key, then it's a 1, 0, 1, right? It's an optional, okay? But in this particular case, right, if we have just a plain old foreign key, then it's just a star, right? Plus, then all the attributes that you have in the table, right, they are added as attributes to the class, right? So all the attributes, right, are added to as attributes of the class, minus, right, any foreign key or primary key. They are not captured as attributes. They're captured using this association over here. Make sense? Right? There are a whole bunch of limitations to this algorithm. There's tons of things that you can't do, but we'll deal with some of those limitations a little later. So if you apply the algorithm starting from this set of tables, right? You end up with our class diagram that we would expect, right? So it does work with our simple little tiny toy example of a class diagram. Now it might be that especially if you need to do design, right? If you need to do design, it's definitely easier to do it in the diagram, right? In the as an image, right? And many tools allow you to do these things, right? Where you can point that tool to a relational database, right? MySQL or whatnot, right? It will reverse engineer that class diagram and that relational database, right? It will reverse engineer what the UML diagram would be for that relational database, right? It's oftentimes much easier to understand what the database is doing once you have a graphical representation. And some of these tools are very, very powerful in that you can make a change in your graphical representation, push a button, and it'll go back into the relational database and make all the changes, right? Maybe change the data types or change the foreign keys or add other fields and all the constraints, whatnot, right? But those changes are so much easier to be done at the graphical representation. Some of these tools are very powerful. You can export anything. You can go back and update, re-update the database. Or you can press a button and it'll generate a whole bunch of Java data models or C# data models, right? That represent those relational models, right? That it can then interact with one another. Very, very powerful, very expensive tools. So it's oftentimes easiest to convert into a UML diagram, make your changes, and then go back and regenerate the table. Class diagrams are definitely much easier to understand and work with than your diagram, than your relational. So what about going the other way around?